So, so far, we've been working with the beginning of the year, we worked with kinematics, and kinematics pretty much describes how things move, right? We analyze the behavior of an object that's moving. We never really talked about what caused the motion. We never really talked about who made that move or what agent is responsible for making that object move. But we just know when it moves, we analyzed it. Okay. And we basically call that kinematics, study of motion. Then the second major unit that we worked on were dynamics. And dynamics pretty much teaches us what caused that motion, right? And that motion was caused mostly by any kind of push or pull, right? So we talked about forces in dynamics. And dynamics pretty much gave us an idea what could cause object to move or what is the agent that's making object either move, slow down, or change its emotional behavior, right? Now comes energy, work and energy, and we're going to combine pretty much what we talked about in kinematics and then dynamics and combine them together to get another dimension out of this deal. And it's called work and energy. All right. So now we're going to combine kinematics and dynamics. All right. So when you talk about energy, right, energy means motion in mechanics, right? So whenever you have some kind of motion, you could think of it as it has energy. Okay. Um, and when it has motion, that motion means it has speed, right? So more speed an object has, the more energy it carries. The direction of this object's energy doesn't matter, right? Energy, believe it or not, is a scalar quantity. Therefore, no x hats, y hats, and z hats. Okay? So it's not a vector. Energy is a scalar quantity. Now, energy can be transferred to an object, right? And when the energy is received by another object, then object speeds up. Okay? When energy is transferred away from an object, the object slows down. Okay? And I could tell you exactly how you can see that in real life. Okay? Now, energy also comes in many different forms. It doesn't always have to be, right, just speed. It could be other forms such as thermal energy, like heat, or it could be location of an object in height, and that's potential energy. All right. So there are many different types of energies that we can talk about. So how is this energy transferred? Well, when forces act on an object, making them speed up or slow down, thereby transferring energy to them or from them. So depending on how the force is applied and which direction the force is applied, the energy can be either taken away or put into it. All right. So work is equal to energy in physics. So if we do any kind of work on an object by applying force on it for a certain distance, then we are putting some energy either into the system or away from the system. All right? So it is energy that a force produces when force pushes or pulls on the mass. Okay? So here is the mathematical definition of work. Now, work, otherwise known as energy, is a dot product. Now, dot product is something that we're going to be talking about, okay? It's a mathematical operation of multiplying two vectors, right? It's called scalar product rule, right? So when I dot these two vectors, I get a scalar quantity, right? And the vectors just go away, okay? By mathematical definition means their triple equal sign means it's really, really equals to, okay? Mathematical definition of a dot product of F vector dot displacement vector can be defined as the magnitude of the force times the magnitude of the displacement times the cosine of the angle between the force and delta x. Now, cosine of the angle between the force and delta x has to be measured from a common point, okay? Now, what I mean by that is I draw the force vector and the displacement vector from a common starting point. So even though they may be separated, you would redraw them and bringing them together. And I'll give you more examples of that soon. All right? And the angle between the force and delta x is what this theta f comma delta x is. Okay? So this is the definition of a dot product of force and displacement, which is equal to work. All right? So work is equal to energy that force transfers to or from an object as an object moves over a distance delta x. All right? So if it doesn't move certain distance or certain displacement, then it doesn't do any work. All right? All right. So let's take a look at some examples. Example 1. A race car is sitting on a track when a force of 1,500 newtons to the east is exerted on it, which moves it 10 meters to the east. So here's my race car. Very boxy, but it's very safe. Okay? And force of 1,500 newtons is applied to the distance delta x of 10 meters. So what is the angle between F and displacement delta x? Well, if the force is being applied in the east direction, the displacement is also in the east direction. When I draw these two out from a common point, right, it looks like here's a common point, and I'm going to draw my F, and I'm going to draw my delta x. They are right on top of one another. So the angle between these two, right? So the theta between F and delta x is equal to 0 degrees. Because there's, right on top of one another. So what is the work done on the force, right? By the force. So here we can say, all right, work is equal to, right? We can say F dot delta x. So the force, the magnitude of the force, right, which is equal to, well, let's put that in there, which is equal to the magnitude of the force, right, times the magnitude of the delta x times cosine of the theta between F and delta x. So we can say the force, the magnitude of the force is 1,500 newtons. Delta x, 10 meters, times cosine of 0 degrees. We know cosine of 0 degrees is 1, right? So the work is equal to 1,500 times 10 will be 15,000 times 1 is just 15,000, right? And the unit will be Newton times meters, or Newton meters. Now this is how much work was done on that race car. All right. All right. Now the same race car is moving down the track to the east when force of 500 newtons to the west is exerted. All right. So even though you're applying a force of 500 newtons, right, the car will continue to still move in the east direction for 20 meters. Okay, so now if we were to look at that same race car, this car will be still moving in the east direction. So my delta x is 20 meters in the east direction, positive 20 meters. And the force will be acting in this way, right? Negative 500 newtons. I should put x heads down so that we can give directions to this, make it legitimate vectors, right? So now if we look at this and draw our vectors from a common point, right? So here's my common point. So here's my force vector going towards west. And here's my displacement vector going towards east. What is the angle between my F and delta x? This here looks like 180 degrees. $180 is the angle between, right? So this is my angle theta. Right? So when we find work now, my work is equal to, again, right, F dot delta x, which is equal to the magnitude of F times the magnitude of delta x times the cosine of the angle between F and delta x. Therefore, force is 500. Now, don't forget, this is the magnitude, so I don't have to put the actual direction in there. Right? So, force is 500 newtons. Delta x is 20 meters times cosine of 180 degrees. Well, cosine of 180 degrees is negative 1. So I automatically will get my work to be negative, right, 10,000 Newton meters as my work done on the race car. That negative 10,000 Newton meters means that's how much energy is pulled out of the race car, taken out of the race car. Okay? So obviously, if this thing is moving this way and you're applying force that way, it's going to slow down. So when it's slowing down, energy was taken out. Okay? All right? I hope that's an easy example, but very important fundamental example. All right. Next. So let's talk about this dot product a little bit more. What if this thing's not acting only on the x-axis? What if it's acting somewhere along the, I don't know, 2 dimensions? Okay, hold on one second. All right, so let's take a look at two-dimensional dot products where we have force and delta x not acting in x-axis. All right, so here, how to take a dot product of any two vectors. Draw a vector from a common origin, like we did up here, right? Take angle between vectors, which we did here. Here, I mean, there was no angle. There was only like 0 degrees because there was no angle between them at all. Here, it was 180 degree separation. Note, must be between 180, 0 and 180. So you can't go beyond 180. It cannot go beyond 180. All right. So let's say if this thing were like, like this, then you just measure this angle here. Or if this thing were like that, you measure this angle here, not the big one, right? Not the coterminal angle. All right. So here you multiply, the force and then delta x and the cosine of the angle with no x hat, y hats, and z hats. All right. So let's take a look at this example right here. So we have a force, 10 newtons, acting 35 degrees from the x-axis. And we have delta x moving along the x-axis for 25 meters. All right? So the angle between F and delta x is 35 degrees. So we could write that down. So theta between F and delta x is equal to 35 degrees. Force is 10 newtons. Delta x, 25 meters. So work is equal to, right, F dot delta x, right? So F, again, work is equal to then the magnitude of F, right, times the magnitude of delta x times the cosine of the theta between F and delta x. So here, my force is 10 newtons. Delta x happens to be 25 meters times cosine of 35 degrees. So if we take our calculators out, and then we can say, okay, 10 times 25 times cosine of, make sure your calculator is in degree mode, okay? So if it's not in degree mode, you're not going to get a good answer. So work now becomes 204.8 Newton meters. No x hats, no y hats, no z hats. It's just 204.8 Newton meters. All right. So that wasn't that bad. Right? So let's take a look at this dot product, John, a little bit more in detail, okay? Now it's easy enough to see the dot product when things are just in 2 dimensions. But sometimes it could be in 3 dimensions, out in space, So my displacement vector can be in like 3-dimensional space, as well as my force vector can also be in, 3-dimensional space. And then it's really going to be hard to measure the angle between them, right? So we could actually do these dot products in a Cartesian way, which means you don't even have to like draw them out. You could actually just do it mathematically. All right. So let's take a look at dot products or scalar products a little bit more in detail. Here's the definition of a dot product. Dot product is a magnitude of two vectors multiplied together times the cosine of the angle between them. So that's what that we just talked about. This A vector dot B vector is read A dot B. Then by definition, A dot B is equal to AB cosine of theta between A and B. Note, the dot product of two vectors is a scalar quantity, not a vector quantity. So what is the geometric interpretation of the dot product? It just means if I'm multiplying two vectors magnitude by the cosine of the angle between it, if I were to project my B vector onto my A vector, right? So this, let's say this is my B vector, and this is my A vector. If I were to project my B vector onto my A vector, which means if I find the component of B along my A, right? So my B component along the A, like BA vector, this is really nothing more than the cosine of this angle theta. So this BA is equal to B times cosine of the theta between A and B. Or similarly, if I were to project my A vector onto my B vector, this component of my A along my B vector, so A along B, this is just the component of my A vector along my B axis. So my A, B component is A times cosine of theta A and B. So you're just multiplying the components of each other's along the vectors that you're multiplying. All right. So don't worry about this. We're just showing you visually what that really means. But we're going to be just doing this mathematically without going through trouble of drawing all these out. Okay, so we can think of A dot B as A times B cosine theta, which is just the component of my B vector along A, or B times the component of A vector along my B axis, which is A cosine theta AB. So these are all same things. So we're just either multiplying this magnitude times that, or this magnitude times that. Okay, that's all it means. So let's take a look at an example here. Let's say I have two vectors now, right? I have vector A, which is 5x hat, vector B being 5y hat. Okay, so if I were to visualize this and draw this thing out, let's draw my A vector. My A vector is 5 units long along the x direction. So here's my A vector. My B vector is 5 units long in the y direction. What is the angle between, what is the theta between A and B? Well, x, y. We know this is 90 degrees, right? So by definition, if I were to do A dot B, this is nothing more than A times B times, right, the magnitude of A times magnitude of B times cosine of theta between A and B, right? Therefore, my A, 5, my B, 5, times cosine of 90 degrees. That is then nothing more than 25 times cosine of 90 is 0. Therefore, it is 0. So whenever you are dotting something that is perpendicular to one another, you will get 0. Okay? You will get 0. So here, if I were to do 5x hat and 5x hat, now we have a different story. We have two vectors on top of one another, right? So here's my A vector. Here's my A vector. And here's my B vector. If I draw on top of one another, it's kind of hard to see, right? So here's my B vector. So the angle between them is 0 degrees. In that case, what do I have? So my A dot B would be then, right? A times B times cosine of theta between A and B, right? Therefore, 25, well, 5 times 5, just 25, right? Times cosine of 0 degrees, which means cosine of 0 is 1. So this will be just 25. All right? So if I were to just dot the unit vectors, like x hat dot y hat, it'd be 1 times cosine of 90. Right? So here, if I were to do x hat dot x hat, which would be 1 times 1, because x hat is just got 1, magnitude of 1, because it's a unit vector, dot x hat, which is magnitude of 1, right? So this will be simply 1 times angle will be 0 degrees. Therefore, it will be just 1. Because this will be, so if you were to say x hat dot x hat would be 1 times cosine of 0 degrees, which is just 1 times 1, which is just 1. What about x hat dot y hat? Well, x hat dot y hat, we should already know this, which is 1 times cosine of 90 degrees, which is 1 times 0. So that goes to 0. Boom. X hat dot z hat. We know that's going to go to 0. Because x and z axis will be 90 degrees. Y dot x, 0. Y dot y, 1. Y dot z, 0. Z dot x, 0. Z dot y, 0. Z dot z, 1. So only the ones that are basically dotting to its own direction are the ones that's going to survive. But the ones that are dotted with anything perpendicular to it or orthogonal to it is going to go to 0. So this actually is very helpful. So when you dot something, you're only going to get these remaining. All right? That means if I were to have two more general three-dimensional vectors, let's say I have an A vector that is ax x hat plus AYY hat plus AZZ hat. So my A vector is this. And my B vector is BXX hat plus BYY hat, BZZ hat. When I dot these two vectors, I have to, right, literally do a triple FOIL, right? Curses, foiled again, right? So what I'm doing is I am doing AXX hat dot BXX hat. So first thing I would do is I would do this dot this, right? And that will be this. Then I would do this dot that, right? That will be this. Then this dot that will give me this. Then when I do this dot this, I'll get this. And then this dot that, I will get this. And then this dot that will give me this. Therefore, okay. Guys, can you hear me okay? All right, something's going on with my Teams.